So take it away.
All right. Thank you very much. Does it work? Some of you may think you're having a déjà vu because you probably have already seen this slide, so it's slightly different because there's this 2016 written here. So you're not going to get the same talk from last time. And as Heraclitus, the philosopher, said, you cannot actually go down to the same river twice. So the same thing is with the state of D at Weka. Let's see what we're going to actually talk about today. So I'm going to remind some of you what is Weka, what do we do at Weka, and then what has changed since I left off last year from the conference. I want to give some examples showing why D is such a great language for the kind of things that we do at Weka, because I don't think there are enough good examples for why D is great as a systems programming language. And then we're going to talk about the challenges that we have and how we can slightly improve the language. So about Weka, we are still in stealth mode, so I'm not going to say anything actual about what we're doing. So the first one is the most buzzword-compliant sentence we could create about Weka. You can read it your own. There's no way for me to repeat it. The engineering is based in Tel Aviv, though all the commercial stuff happens in the US, so no use selling anything in Tel Aviv. We're VC-backed. We're still in stealth, but it may warm your heart to know that there are some very large companies, billion-dollar valued, with great names, actually running decode in production, doing very important stuff. Hopefully, in the future, we'll be able to reveal these customers when we're out of stealth. We're probably not the biggest code base, but I think that we are the biggest single executable compiled out of a large code base. So we have about 200K lines of code, and we break them to 35 packages. So still being buzzwords compliant, I'll try to explain a bit what a storage system is, because most people don't understand. But like from a bird's view, people have petabytes of data, and they care about all the bits. They have to be the exact bit that they stored, and they have to get them the same order, and it has to be lightning fast. So that's actually a non-trivial problem to solve. We basically keep the state for the data centers, because everything else reboots, and the storage brings it back to state. So the storage is the single component of the data center that has to be there. If storage broken, things like they deteriorate and you're getting funny calls. So we don't want to get funny calls. So really high performance, we need to get IOs back in microseconds. Microseconds isn't a lot of time. There aren't many cycles with each microseconds, and we have to repeatedly do it all the time. But there are lots and lots and lots of features. Customers like features, so they have to be implemented, and they have to be implemented in a way that the next data path requests are going to come up blazingly fast. So it's not a trivial thing to do, but I'm going to show here that D actually does a very good job of fixing some of these problems. We have low-level interactions with hardware devices, with the kernel. We have assembly code. So it's a very interesting systems programming language. And also, storage systems tend to be huge projects. So we're only at the beginning. We're just maybe a largest project, but within time, we'll end up getting to be a huge project. So we have to be ready for that. What we're doing, we're software only. We run in user space. The way we respond quickly is that we leverage complete cores. We run 100% of the core in like a polling mode. We have a reactor. Everything we do is very memory efficient. We cannot waste cycles, loading time from memory to caches and these kind of things. And everything is zero copy. If you start copying memory around, you already lost, because copying memory is like insanely expensive. You have to read all the memory you are copying. Mostly garbage collection, allocation, free. We have lots of lock-free data structures, and sadly, we have our own proprietary networking stack that allow us to do what we do quickly enough. So, where did we get since we last met? There is a huge green checkmark here, so I think it means that we should give our all like a huge thumbs up, because last year we had lots and lots and lots of really big problems, and we weren't even sure whether they're solvable. So I'm very happy to say that we don't have any more showstoppers. And as I said earlier, we're already in production at real customers. It means that there aren't any more showstoppers. It doesn't mean that we can go to sleep. There is quite a lot of extra work we have to do, but as it is today, D is usable for our kind of system, which is great. And one of the main reasons I want to be here is actually let the world know that you can implement a complex systems programming solution, and storage is most probably one of the most complex problems to solve in D, and do it successfully. So hopefully, lots and lots of people are going to watch this presentation, and when they make decisions, I want them to remember this sentence. You should pick D for your systems programming projects. And actually, I do get quite a lot of feedback from my previous and got like private questions. So people do watch it later. It's not like down to the ether and dies. We have great productivity. One of the great features of these that it has a great expressive power, and I think being able to model easily and beautifully and have a readable code, these aren't just academia things. These things actually help us create usable code, and I think much quicker than our competition, which basically this is what we care about. Another great thing of D is that it allows us to start prototyping with the language that we're actually going to implement the feature. So we start implementing or prototyping a feature, trying to find the hairs in it and the problems in it. And instead of doing like initially in Python and then porting to C or C++ or whatever, we can do it in D. We can like allocate from the GC like there's no tomorrow. We can do like many cut corners. But once we got the functional part working, and we didn't have to bang our heads around it, and it really simplified our problem, then we have to start thinking, all right, the feature is basically working, but it's not usable. How we use this code and we make it into a usable feature. And I'm currently not aware of any other programming language or an environment or whatever that allows you to prototype and then use that prototype for the end result implementation, which is, as I said earlier, very productive for us. I don't see us getting our turnover in features as quickly as we get in D with basically any other solution, and we do get great performance. So D is a great candidate as a systems programming language. We can use tools like perf, we get the assembly, we can optimize it, and all the normal optimization trick known to systems programmers work very, very well and efficiently in D. So I think if I have to summarize the last year, is that we were actually convinced that choosing D was a very good move, and it's going to really be an important part of our technological success. So let's talk about what happened on our compiler front. Actually, coming to DConf last year was one of the best things that happened to me, because right after my talk, David Nedlinger here came over. Maybe you want to stand and get the thumbs up. So, and he told me, your problems are absurd. I'm going to help you solve all of your problems. So with David's help and with the rest of the LDC's team help, actually, we were able to solve all of our compiler and the D runtime actual problems. So I think we couldn't have reached where we are today without the LDC project, which I think it's amazing, and they should get all the support that you guys can give them. Currently, we compile by package. That was a problem we had previous time. We're going to get to that later on, but basically what we get is a better RAM management, so we can compile, which is important. And we get slightly better parallelism. Another very important thing, and I think that Andre talked about it last year, like a couple years ago, you picked up D, you tried doing things, the compiler would crash. It's not fun. So I don't think we've actually experienced a bug in the generated assembly, but writing your code and having the compiler crash isn't fun. And I think when you have new people now picking up D, when they try writing code, they bang their heads at the keyboard, they get something, they compile it, it compiles, which is a very important thing. So currently, it's probably much stable than what C++ used to be like 15 years ago. And nobody said that C++ isn't stable back then. So I think it's from that perspective, leave the first 5 minutes really primed for wider adoption. Another great thing we get from LDC is that running our systems in CI, we compile in release mode, but we do get asserts, which really helps debugging, because we don't want to keep most of the asserts in the actual production code, but when we are developing the code, these asserts are very important. So our LDC status, we currently get, I think, a bit over 100% performance improvement LDC compiled in release versus DMD, which puts us in great land. We're still stealth, so I'm not going to give any performance figures, but we're happy, I can say that. One important thing that also answers a question that Walter had, when we compile release, we actually use huge machines and we compile all the object files together. So when compiling all the object files together, we actually let the compiler have many more inlining opportunities. So when LDC compiles in release mode versus LTC compiles in release mode, having all the libraries together, we get about 30% performance improvement. So there's a question over there.
I have a question. What does fiber switching based on registers mean?
I'm going to get to that.
Okay, sorry.
So inlining does provide quite a lot of optimization, and just let me finish. When I see some code that is a hotspot in perf, and many times we try to understand why an inline would be great, is that you see that the two functions are fighting for the register. So what you actually get when you inline is that the compiler gets the bigger picture. The compiler is able to use the set of register it has across a bigger chunk of code. So many cases, I didn't see your code, but probably you're writing to register, then you're calling a function. That function starts by pushing all the other registers to stack. You're stalling, because now you're forcing the CPU to do a write through and wait for it instead of a write back. So these are the reasons that, some of the reasons that inlining gets much better. Yes, please.
Have you tried link time optimization with LDC? I'm not sure if it works, but...
So basically what we get is link time optimizations, because we let the compiler have all the information while compiling. We don't compile each object on its own. We actually compile the whole thing together, which does give us the LTO fill. We are going to implement LTO later within our build system, but that's because we want to have inlining opportunity with some C libraries that we're doing. And then we could LTO the C libraries, LTO our decode, and then get everything better inlined.
And also profile-guided optimization. I think with DMD it boosted like 20% or something. So that's like something you should also try if you haven't already.
All right. So let's talk quickly about the rest of the points, because I think they may mean less for the other guys. But fiber switches based on the local storage registers and instead of the P threads, we actually don't like moving fibers between threads. And if anyone wants to repop it again, I can reiterate that the fibers model with moving fibers between threads is actually weaker than when you allow the move, no matter what funny thing Go's doing. And actually, if you look at Ali's presentation from yesterday, if you allow the fibers to move, it would actually be incorrect, because you'd have to protect your shared knowledge. So in our compiler, we don't let fibers move. It's faster and it's more correct. So we don't GC allocate when we handle exceptions, and thanks Smithen for it. You're actually going to see him tomorrow talking about other things, but he really helped us here, again with David's help. We have a slightly different version of leap unwinds that uses the dwarf information, so we don't have to use the FP anymore, so it's slightly higher performance, but also when we have a stack that goes with a C library in between, we can get the full stack. Because when we use the C libraries, of course, they don't come with a frame pointer. Debug builds are slightly better optimized. And some of you know it. We cannot really build currently with DMD because there is some template instantiation issue that prevents us to do it. Hopefully, I think, discussing it between the group and the last couple of days, it will get pushed up to DMD. So DMD will be able to build our code. We are able to put things at specific sections, so it could help reducing GC collection time. We aren't doing it yet, and it does help us to do some tricks that we talked about the previous time, but if anyone else needs it, it's part of LDC right now, and we have the ability to statically link. So we don't have to come up with different utilities, for the Ubuntu 14.4 and 15.10 and the Rail whatever. We just compile a single utility once and we distribute it, and it's amazingly great for us. We don't like the GC. You may have noticed that. We don't like the GC, and previous talk we actually had a lot more struggle with it. And I will now describe what we're doing. Previously, we just collected like every 30 seconds. It was a lengthy process because we went through a lot of memory, and also it could get a large cluster of computer in sync, all waiting almost together, so increasing wait time over and over and over. And actually, you cannot get microseconds latency where collection time is milliseconds. Impossible. So what we're actually doing now, we've exposed some private parts of the GC, and we know what are the pool size and what are the used size, and we will actually call the collection if we've aggregated too much memory. So right now it happens infrequently, several times in an hour, like 2 or 3, and it's never correlated between the different servers in the cluster, so it's actually good enough. But the important thing to understand about GC and why we actually cannot even use it for our control code is that the biggest downside of the GC isn't the collection time. We're able to tame the collection time. We can probably reduce the 10 milliseconds. The easiest drawback, let's say we have a control path thread. That thread is trying to allocate some more memory. It's calling malloc, brk, whatever. Now, the kernel is short of memory. This happens. So now we have a control path thread asking for more memory. The kernel is low on memory, so it either has to write one of its dirty pages or swap out some process, do some very, very lengthy work. So getting more memory when the kernel is low on memory is going to end up way, way, way longer than the 10 milliseconds, and it's going to stall the whole process because it's changing the memory ranges for a very, very long time. For us, almost an infinite amount of time, which means that also for the control path jobs we're doing within the same processes, we cannot GC allocate, and we have to use the same tricks of allocating from pre-allocated pools and the other systems programming tricks. Exceptions and the garbage collection. So you may have noticed, but exceptions are a class. You have to allocate them, and they used to come from the GC. So our LDC has one main difference in the runtime. The runtime doesn't allocate while handling the exceptions, and our code doesn't allocate while throwing them. So there are two things that we have to take care about within our code is that when creating the new exception, this is basically what we're doing. This is the static allocation. I don't know how many of you are aware of this syntax, but it's, I would say, godsend or Walter sand, but it's amazing. So when you do something like this, you actually get the exception instantiated and garbage collection allocated when the process goes up. So we don't care how much our process takes to go up. Well, within reason, seconds. But until we're up, it can take very, very long seconds, and we're okay with it. So we pre-allocate all of our exceptions when we go up. And then there is another thing. There is this trace info class that currently we have a one per fiber. So when something throws inside the fiber, we already have the trace info class that represents the stack. We made sure that the rest of the handling code doesn't allocate, and we already have our own exception, so we're good, which is almost true. We came to this mode after we've already had quite a lot of code, and we've came to places where we have code within scope exits that actually throws an exception. And then catches it. It even catches it or it doesn't catch it, it doesn't matter. So if we have a case within a scope exit that catches it, we are actually going to override the actual exception that happened, and we don't know it anymore. There is no good way for us to do chaining within our current runtime. One solution, which could be a good one, is say, just go over all your scope exit code, break it to a success and failure, you know you're safe. But now we have to go back to my 200K lines of code and see what's going. So some improvement we'd like to have, and not very difficult to add, is to actually be able to know whether there is an active exception being handled, and then we can just treat it differently. But like 99% of this horrible exception experience we had last year was solved for the good part. So let's have some code tidbits, as I said earlier, the things that we do in D that we really like. So this is like, you're not getting like a full code, these are just the tidbit. This is what we call a network buffer PTR. We had a very strange bug, and we assumed it came out of our networking code. Actually, it came out from faulty hardware, but that's not the reason it's here. The reason it's here is that we have something called a network buffer. And all over the code, since we are zero copy, we just move around these kind of objects. This is our zero copy way of moving memory around. So we move these pointers. We assumed someone's holding a stale pointer and it's writing to it when it's illegal. So how do you do it? So actually, Tomer here, with quite intelligibly, what he did, he created a type called network buffer PTR, which is a pointer to a network buffer, and it uses the up 16 bits. You probably know that working on a 64-bit processor, you don't actually get 64-bit pointers. You only get the 48-bit. So you got like a whole 16 bits to do something with. So what Tomer did is that he did use these 16 bits in the pointer to keep a generation counter. So whenever we got a buffer from the pool, we'd increase the generation, and then we didn't actually hold a pointer. We hold like a network buffer PTR type that has the actual pointer and the generation. We have an alias this that says that you only call get to actually use the pointer, and then whenever you are trying to actually access the pointer, you compare it, as you see here, you compare the address and the magic mask with the pointer generation. So it's not good for performance because we may be changing store operation with a load operation. We have to read the gen, and then we also had to do like lots of prefetching and other things to actually get it work with reasonable performance. But the thing is, if you don't care about our performance, then you have these little bugs. It's very easy to actually add ways to solve them and try to find them within your application. So this was a very, very, very nice trick to be able to find a bug, and actually for most systems that they don't care about performance as we do, this kind of solution can actually be part of the normal code base, and you're going to be way, way, way safer. Just one little thing about it is that implementing it required a lot more work than initially we assumed, because null had a problem being implicitly casted to the network buffer PTR. There is no way for a type to say how you can cast things to it. So we actually had to go through all of the code, find all of the places when there is null, and replace them with something that you could assign to a network buffer PTR. So like sort of an improvement would be to let a type, just say, this is safe. So explicitly. So it's not like we're going to harm anything, but it could make this kind of modification much easier. Another example that we're using in multiple cases is going through either enums or struct members and doing something with them. So, for example, here, part of our networking code, we make sure in several places that we actually implement the handlers for all kind of packets or other things. And when we interact with C code, the problem is that sometimes changes on either part breaks the ABI. So what we're actually doing with the D part, we enumerate the members, and we ask for the size of and the offset of our C members, and then we have handwritten code in the C that returns these numbers. So the C part isn't automated, but the fun part about the D part is that we get the D part of it, just because we have the compile time introspection so much easier. So this is another trick. If you are binding D and C, you should make sure that all the structs that you share actually have the same offset of and size of for all parameters, because probably similarly to the floating point discussion, you're going to have a fun night. Another very nice trick that we like is using flags. We have lots and lots and lots and lots of flags, and mostly testing flags and setting flags. You know, you're keeping lots of state within bits. In int, you may do it, you may not, but this always ends up with a really clunky code. So what we do here, we have actually an enum. It says what bit each flags get, and actually for a similar solution, we have even a better way. We just say what they are, and then another code assigns the exact bits to them. And then when we test for them, we can just ask what the bit to ask for, and when we set them, we either turn it on or turn it off, but then the code ends up being very, very, very easy and very, very, very readable. And the nice thing about D is that compared to practically every other systems programming solution, we get a really readable code. So with many other solutions, you're not trying to improve these cases because it's like a catastrophe all around it. So what would this help? But because it's a lot easier to write beautiful code with D, and that's easy to write and also easy to read, then these kind of things make sense. And actually, story I would get like people coming over to me with C++ problems, asking me why it's not working. And I used to be able to come up with answers quickly. And a guy came again like a month ago, and he asked me a question. I was using D so intensively in the last few months that it's getting too hard to really think about all the C++ problems. So I think it's like a good example that we are doing something right here. Another thing that's probably only possible in D, which is amazing because we have these higher level features, and then they let us do things with more performance. People say C++ is great for performance, but you cannot do it in C++. So what are we doing? Here we have a sum container, and we want to come up with an efficient implementation for it. So this is a container that's associative array-like. It has a key and a value. So we have a joined key value together, and we check whether they fit in a cache line. Because if they fit in a cache line, we're just going to put them together and go over them within the memory. But if they don't fit in the cache line, we'd want to put just the keys together so we can find them quickly and offload the values to somewhere else. With D and the static if and the ability to ask a size of something while you're compiling, which we take it for granted, but this is like insanely fun. It's easy, but I don't think you can do these kind of things with any other kind of implementation, which is great. This shows that the fun parts of D even add performance. So, we're very happy for this part of until this part of the presentation, but it's not all fun. We also have some challenges, and currently our biggest challenge is the amount of time it takes us to compile, because we have a big project, and we don't care about the release. We don't care how much release compiles take. They take like 40 minutes, maybe more now, but it's okay because it's a robot waiting for them to happen, and then the robot is doing the other things. We care about debug compiles where there is a human being waiting for it. So we currently have about 200 lines of code broken into 35 packages. Actually, we break it into more compilation packages than we actually have logical packages, so we can parallelize better. And it takes like 4, 5, 6 minutes. So it takes like 4, 5, 6 minutes on our current front end that we work on, the 68.2, which is our equivalent to the .17 for LDC. And actually, we have Johan here. You can give him a hand. He's taken the newer, now there's also 71, but he's taking the newer 70.2, imported some changes, changed LDC to compile LDC himself with PGO and LTO, all the things together, and actually we're able to get the time lower by 35%. But our biggest problem that it's still like 3-4 minutes, and when engineers have to wait 3-4 minutes, they start doing something else. So we would have liked people to have short cycles when they just test something and see what happens, but this is not currently what we have, and I think we want to make sure we improve the compile time. So one option is to add parallelism, but the most important thing that while doing these changes we have to remember is that we want to have incremental compiles. We want to find like a trick or whatever to do incremental compiles quickly, because of the way that the current semantics work. A programmer changed like 20 lines of code, but these 20 lines are within a package. That package gets completely recompiled, but because the package has lots of files, many other packages may have to recompile, and then you recompile yet all these other packages, and now most probably the rest of the project rebuilt. So we're changing like 20 lines of code, and we're waiting for a complete compile, which is a problem. So we should come up with incremental compilation support, hopefully a solution that has a relation to centralized caching. So let's say another developer just built, we can enjoy the outputs of that build and make sure it happens quicker. Because the last thing that we know, the most precious resource we have are smart engineers. And we want to get as many cycles out of the smart engineers as we can. So letting them wait isn't like a good option. Another problem that we have, they may actually contribute to the long compile time, is the symbol issue. It may be related, or probably related, to Voldemort types. You can read it on the forum. It may come from another reason, most probably the Voldemort types. But out of the almost 100K symbols we have, by the way, this is for the compiled, we have some modules that before they link have more than 150K symbols. So out of the 100K symbols we actually have at the executable, over a meg, we have almost 10K symbols. Over a K, it's almost 10K symbols. Over half meg, it's 100 symbols. We have 62 symbols bigger than a meg, and actually quite a few of them are about 5 meg long. So you may be saying, if we somehow get less information in the symbol, it will be less debuggable. But guess what? A 5 meg symbol doesn't help you debug anything. It's useless. So if you get more than 100 characters in the symbol, or let's say 200 characters in the symbol, it's probably useless. You're not going to get anything out of it. So I think that this is another big problem that we have to support, because running perf on our executable is insanely slow. So actually the perf collection is okay, but reading the results is like, you wouldn't believe the pain. Launching GDB takes long minutes, while GDB is crunching all the symbol tables. So NM crashes. Who would believe? It's the tool that should get the symbols. It crashes. So actually to get this information, I use objdump. So objdump doesn't crash. But I don't want to know it. Why should I know that objdump doesn't crash on the long symbols and NM does? It's like insane. So this is something that we have to solve. There is a partial solution by Johan at our new front end that hashes the solution. It's working, it fixed the problem, but the other problem that we have is that hashing takes time, and the extra time used for hashing is actually longer than the time we save linking. So now our compilation time are even longer. So these two actually work together. And there may be a case to say that if the front end didn't generate such long symbols to begin with, the compilation could be made quite shorter. So this is another thing that
You can use the address of the symbol to export.
Actually, this is one of the things that really helped, that got us this 35%. The trick that Walter just described in the morning is part of the 35% improvement, I think, that we got over here. All right, another thing that we would have liked to improve is that we would have liked to use the Phobos algorithms, but the Phobos algorithms force GC. Why do they force GC? It's a good question. You don't really notice it, but there is a delegate over there. So if hopefully you can read the code, but there is like a filter checking for undervalue with the GC and without GC, and then we multiply by a value, do a map and a filter. So we have our X filter that doesn't use the GC, and basically what it does, as you can see like the map example, it creates a struct on the stack, it puts the value in that struct, and then we do it locally. So if we had a way of forcing the compiler to trust us that this delegate is going to be scoped, then the compiler could have done it for us. Because the compiler could very easily create that struct that we have to go and do for each algorithm that we like, and actually put it on the stack for us. Yes, please.
We at Sociomantic, migrating our code to D2, have the same concern. You're talking about a dynamic closure, I guess.
Right.
We have exactly the same concern, and there is a way you can declare scope delegate, and then the compiler will trust you. Maybe I think this is something rather recent, but.
Or I think that we did try to use the things they ended up GC, for our case, they ended up GC allocating anyways. We can look at it again, but I think that we did relook at it fairly recently, and we couldn't.
I was very pleased to learn that. From Matthias Lang and Michael. I was very pleased to learn that this has, I think, rather recently been implemented.
Okay. No, like sadly, it helps in many of cases we have with like closure allocations, but not in all. So scope delegates don't actually work reliably. So like, it helps sometimes.
Yeah, I think the last time we tried the scope, we couldn't actually convince the compiler that it's scoped for all of the cases. And still, since it doesn't always work, it's still easier for developers to use our X version that doesn't use a delegate. But it's like a whole bunch of code that we'd be very, very, very happy to delete. As Walter said earlier, when you delete like 200 lines of code, you're very happy. We actually have a word for it at Weka. It's called kodelitotsin. It's like a joke. But this is the stuff that your mind generates when you delete code. So if we get this implemented, we will be able to delete quite a lot of code from our repository, which is always a good thing. Now we have some improvement ideas. One thing that could be made better is static for each, because currently people write for each and they aren't certain whether it's going to be static. So there are some tricks. You could put like a pragma message and see what happens, and all the other tricks. So adding a static for each to the language will make everything more explicit and actually solve all this confusion. But something that could really help us a lot more in our generic code is being able to static for each within templates. Because not the generic programming templates, but the templates that lets you work over types, because currently the way of doing it is create sort of recursion. So we have lots and lots and lots of places where we have these recursive templates that are hard to understand, and also have the 500 recursion limit that sadly we hit over there, where all this helper function could actually be replaced by a very simple for each. So putting for each inside template, supporting for iterating over types will enable us and probably lots of other code to be made very, very simpler. And I think simple code is one of the tributes of D, and this is something that could easily be fixed, and the code will be much, much simpler. Another thing that we would really like is have support for transitive user-defined attributes. So we would like to say for a function that there is no way for this function to context switch, because when you're writing fiber-based code, you're calling function and it may stop. So Ali talked about it briefly on his talk yesterday, but it's a lot easier to prove that your code is correct if you know that no one's going to interrupt you for whatever reason. So we would like to be able to mark a function with some UDA, mark that this UDA is transitive, and then force that this function may only call other functions that actually have this transitive UDA. If we could get like a trait that returns the list of functions that a function may call, this could actually become a very easy feature to implement. So all we have to do is add these traits, and we could add support to it. The next step for these transitive UDAs is allow them to prove something over the AST. Actually, we couldn't really get our heads around it to really define it, so this is why it's the next phase. But once you've done it, you could also like fold no GC and pure, no throw, and the other things to it, and make like a really nice generic solution. But the next phase isn't a mandatory, because we can still mark our things and follow them, and it's going to make everything a lot simpler. Not very much different from Andrei's O notation, big O library, which is great. Some other suggestion that would make our life much easier is get a trait for the stack size of a function, because currently we have all fibers instantiated with like huge stack, because some functions that we're going to spawn are going to use a huge stack. But guess what? Most functions don't. So we are wasting lots and lots and lots of resources for something that could be automated. So if we had like a trait that tells us what's the max stack size of the function, and we had the other trait that tells us what other function it may call, we could come up with a pessimistic approximation of the max size that could be there, and then we could have different classes of fibers and actually make much better use of our memory. This is probably another thing that other languages are going to have much harder time supporting, which would be another good case for D. And as I said earlier, we also need the predicate, knowing whether there is actually an active exception going on, so we know what to do with it with our scope exits cases. So we handle them. We handle exception chaining within our runtime. And as I said earlier, hopefully this year we'll be better at it. We could donate quite a bit of our code to the community, and actually, probably, hopefully, push other system programming projects to pick up D, because now there's going to be a lot more infrastructure for it. I'm actually done. So this is a Weka. It's a very nice bird from New Zealand, if you like the birds, and Weka is also 10 to the 30 if you like numbers. So you pick. And